Hello, dear students. Once again, welcome to this YouTube channel. So, in previous class, we have discussed about the magnetic force on a moving charge. Okay, suppose the charge Q is moving with velocity v in a magnetic field B, then the force experienced by that charge is Q times v cross B. Okay, so and that force is maximum when theta is equal to 90 degree. It means v and B are perpendicular, and 0 if v is parallel to the field. Okay, so now today we have to discuss about magnetic force on a current carrying conductor. Magnetic force on a current carrying conductor. See, consider a straight conductor, say for example PQ or AB, whatever may be, of length L, and area of cross section is A. Capital A is the cross sectional area carrying a current I. It means the current I is flowing through the conductor, and that conductor is placed in a uniform magnetic field B. Okay, uniform magnetic field B. Okay, so now when an electric current is flowing through the conductor, it means what? The charges are moving. Then definitely there is a force, that is magnetic force, experienced or acts on the charged particles. Okay, let N be the number of electron per unit volume of the conductor. So it means it is called as electron density. So it means the number of free electrons present per unit volume. Okay, already this one is discussed in chapter number 3 also. Let Q be the charge on an electron. Charge of the electron is Q, or you can say E also, no problem. And B, it's and V B, make it as V, and V B, its velocity. Okay, so now the magnetic force on each electron is F equal to QVB or BQV. This force is on a single electron, remember. See, the number of electrons in a conductor of length L is, okay, total number of electrons is NLA, that is number of electrons present per unit volume into volume. That volume is length into area, length into area. So hence the total number of electrons in a conductor of length L is N times L into A. Cleared? Okay, next, the force on the conductor of length L is, see, NLA times QVB or BQV, because for single electron BQV, if there are 2 electrons, 2 times BQV. So here in that conductor there are N number of free electron density, and the total number of free electrons are N times L into A. So hence the force is NaL times force on single charge. So force on single charge is VQV. So therefore NLA times BQV. See, we can rearrange these, and also we can write F equal to as B bracket NVAQ bracket I. L you can take, sorry. Now in that bracket NAVQ, this one is the expression for electric current in chapter 3. So hence finally getting as, okay, this expression we have already discussed in chapter number 3. So finally we are getting F equal to BIL, F equal to BIL. And one more thing here you have to remember, the current, the flow of current, it means the length of the conductor which is perpendicular to the field. Otherwise we can write that force as F equal to BIL sin theta, BIL sin theta. This one is the magnitude of the force, okay. And the direction of the force, already all of you know. The direction of the force we can explain on the basis of Fleming's left hand rule, okay. See here, next one is magnetic field due to a current element. So in first class of this topic we have already discussed a current element or a current carrying conductor produces the magnetic field, and the magnetic fields are surrounded around the conductor, and that can be explained with the help of right hand clasp rule. When that conductor is clasped with right hand, thumb gives the direction of current and other four encircled fingers gives the direction of the field lines surrounded around the conductor. Here XY is the conductor, carrying current I, So for this Biot-Savart law or Laplace law, you have to take a small conductor. Let you can say that the conductor is AB, and let its length is DL, you can say. That also produces the field, and that one is also having the same current, means same current is flowing through that small conductor of length DL also. So then according to Biot-Savart law, okay, the magnetic field at P, we want the magnetic field at P. So just you have to draw one line which joins the current element and the point, okay. Now the magnetic field dB at P is directly proportional to the strength of the current. If the current is increasing, then definitely we are getting the magnetic field is also more, it means it is also increasing. So hence the magnetic field dB is proportional to current I. Next one is this dB directly proportional to length of the current element. Here the length of the current element is taken as dl, or you can take delta L. Okay, so it means the field is directly proportional to length of the current element. Next one is third one, directly proportional to the sine of the angle between the current element and the line joining the point and the element. Cleared? So here theta is the angle between current element and the line joining between current element to the point, and the magnetic field is proportional to sine theta. It is shown in this figure. Cleared? Okay. Next one is the magnetic field at P or at any point is inversely proportional to square of the distance. So here in this figure it is shown, see this figure. This dB is inversely proportional to r square. Is it clear? Okay. So therefore, by combining these four, and we can write dB as I dl sin theta by r square. dB proportional to I dl sin theta divided by r square, or dB equal to some constant k dB equal to some constant k I dl sin theta divided by r square. Ideal sin theta divided by r square. So here k is proportionality constant. In SI system, the constant k is mu naught upon 4 phi, and its value is 10 raised to minus 7 Henry per meter. This proportionality constant k is mu naught upon 4 phi. Same as in electrostatics, we have already discussed proportionality constant. We are using as 1 upon 4 phi epsilon naught, and here for free space mu naught is called permeability of free space, and epsilon naught is permittivity of free space, remember. So hence the above equation becomes dB equal to mu naught upon 4 phi I dl sin theta upon r square. And in previous class also we have discussed the unit of magnetic field is Tesla or Weber per meter square. How we will get that Weber per meter square means the magnetic flux which is expressed in terms of Weber per unit area, that is area of the unit is meter square. So hence Weber per meter square, or there is a special unit Tesla. Clear? Okay. See, is it clear? Final expression is clear. So simply this Biot-Savart law gives dB equal to mu naught by 4 phi I dl sin theta divided by r square. Okay. So one more term is remaining here. The direction of the field at a point due to current element is proportional to the plane containing the current element and the point. So it means that magnetic field B is perpendicular to the plane of the board. Cleared? If that plane containing the current element and the point. So we can write dB equal to, in vector form, mu naught by 4 phi, this one is the proportionality constant, I dl cross r, vector dl cross vector r divided by r cube, because see, dB equal to mu naught by 4 phi I dl cross r divided by r cube. So previous one is mu naught by 4 phi I dl sin theta by r square. Why here r cube? Means dl cross vector r is magnitude of dl, simply dl, magnitude of r is r. Okay, and already it is perpendicular, means sin 90 is 1. Okay, so divided by r cube, finally we will get the same expression. So the direction of dB is perpendicular to the plane containing dl and r. ಸೊ ಯಾವ ಪ್ಲೇನದಲ್ಲಿ ಡಿ ಎಲ್ ಮತ್ತು ಆರ್ ಒಂದೇ ಪ್ಲೇನದಲ್ಲಿ ಇರುತ್ತಿಲ್ಲ, ಆ ಪ್ಲೇನಿಗೆ ಪರ್ಪೆಂಡಿಕ್ಯುಲರ್ ಆಗಿ ಏನಾಗಿರುತ್ತೆ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಸಿಗತ್ತೆ. ನೆನ್ಪಿಟ್ಕೊಳ್ಳಿ. ಕ್ಲಿಯರ್? ಓಕೆ. In next class we can discuss the remaining one. Thank you.